So welcome everybody to this third and final day of the PIRL conference. Our first two Fridays, I think, have been very successful. At least I enjoyed them. So we're confident that this third day is going to be equally engaging. During the first hour, we're going to have these three talks, which hopefully everybody went and watched the videos. We're going to have them come in and present their summary, which is just a couple of slides or so from each of the presenters. And you can see I listed the three talks there on the slide to remind everybody what they are. And what I think I'll do is have all three of them do their summaries. And if you have questions while you're listening, please type them into the chat window. And then afterwards, I will either read the question or I may ask you to just unmute and engage directly to get a little more live, engagement going. Let's see. So the first talk that we're going to do is from Hanxian. And Hanxian, please go ahead and you can unmute, and if you like, you can start your video. It's up to you. And I'm going to start by putting up your first slide, and just let me know when you want me to proceed to your next slide.
Good morning, everyone. This is Hanxian Huang, a second-year PhD student from UC San Diego. I'm working with Professor Jishen Zhang. I'm very happy to share our project on PIRL towards easier persistence-aware programming, a deep reinforcement learning approach. So this framework basically want to help translate volatile C or C++ source code into the corresponding persistence-aware code. So compared to writing volatile code, writing non-volatile aware code brings more challenges for users to write additional codes to promise the consistency and also enable the recovery after system failure. So it requires users to have expert experience on memory and also have experience on using some non-volatile memory aware library, and also PM-aware programming still require in-depth code changes based on the original volatile code and is labor-intensive and error-prone. So our goal is to close the gap between users and persistent memory to help a new user, assuming who only know how to do volatile programming, to have a crack persistent-aware programming. Andy, can you change the slides for me? Yeah, so suppose the user only know how to write the volatile C or C++ code. So the input of our program, problem is the piece of pure C or C++ program. And the output is the corresponding PM-aware C or C++ code. So example of the corresponding source code and the target code after adding some interface. So in the black box, firstly, we need to choose some correct library API. Here we will choose the PMDK library APIs. And after that, we need to insert the API into the correct place and into the volatile source code. And finally, we need to use some checkers to check and promise the persistency and consistency of the generated program. So here we mainly use the workgram payment check and PM reorder. And to finish this three steps, we introduce a reinforcement learning-based framework consists of three stages. So in the online training process, the network will first encode the input program and then take action to insert the API and get feedback from the checker and update the parameter according to the feedback to learn how to explore the actions to win more positive reward feedback. So that is how to learn how to modify the code based on the library API and promise the persistency and consistency of the generated code. And after the online training, in the offline inference stage, the well-trained reinforcement learning neural network can imitate the human behavior and choosing and adding APIs to help us modifying the program. So I also would like to mention here, we actually also implement a Java translation by implementing the transfer learning. So the transfer learning basically learn from how C or C++ translation works, but because we only have two Java example codes in the PMDK datasets, we still need to need additional dataset to make our model more robust. So if some of you are interested in Java code translation or have some Java code to test, feel free to contact me. And Andy, can you change the slides for me? Yeah, so here's the result. So we can see from this figure that we can successfully generate the code for some micro benchmarks such as tree, hash, array, queue data structure, and also the real-world case KV store. So these cases can pass both foreground PMN check and PM reorder tests and show the persistency and consistency correct. So it means on these test cases, our model can achieve 100% translation accuracy. And we can also find out that generated code on microbench have very similar average execution time of multiple reads and writes compared to the PMDK expert code. We have showed a simple example here of the generated code on micro benchmark. So we can find out actually the generated code is very similar to the PMDK baseline code. And for the real-world cases, such as KV store, since the code has more complicated data structure than functions, so our generated code may lead into some redundant APIs, so brings overhead. But we can at least promise the persistency and consistency correct in this case. So, and our generated code can be further improved to reduce syntax bugs and performance bugs by other debugging tools. And we will try to further improve the framework robust by adding more checkers in the training process. So our work contributes to reduce the study costs and labor on modifying existing volatile data structure and also encourage the use of non-volatile main memory on the existing volatile source code. So that's so much of our framework. And any question and suggestion are welcome. Yeah, thank you for listening.
Thank you very much. Please type questions into the chat for now. As I mentioned before, we're going to go through all three summaries and then we'll answer questions as a panel. So we're in the question gathering phase right now. And thank you, Hanxian. And now our next speaker is Zhangyu, and I'm going to go ahead and advance to the first slide, and go ahead, Zhangyu.
Okay. Can Andy hear me?
Yeah.
Yeah, okay. Hello, everyone. I'm Zhangyu from Huazhi University of Science and Technology. This is a two-page summary for our recent work about lock-free index design for persistent memory. In this work, we propose clever hashi, a quasi-consistent and lock-free hashi scheme for persistent memory to provide scalable query services for PM. Due to the silent features, PM is promising to speed up storage systems. In 2019, Intel released Intel OpenDC persistent memory. This PM product is DIMM compatible, and each model provides up to 512 GB capacity. More importantly, the non-volatility of PM enables instant fail recovery from data in memory. Despite the impressive properties of PM, applications designed for PM should also care for the hardware characteristics. Specifically, to ensure the instant recovery, data in PM should be consistent at any time to avoid the data loss upon system crashes. In the meantime, the limited endurance and bandwidth demand write efficiency. PM index structures are also important for storage systems to provide fast queries. Unlike tree-based schemes, hashing-based index structures map items to flat space, thus leading to constant time complexity for point queries. Therefore, hashing structures are widely used in memory. For large-scale storage systems, leveraging the hardware parallelism to provide high concurrency for terabyte-scale PM data is desired. Specifically, it is necessary to achieve multi-reader and multi-writer concurrency with concurrent resizing. Recent research proposed crash-consistent and write-efficient hashing indexes for PM. However, these schemes suffer from limited scalability due to the expensive log-based concurrency control, making multi-core parallel programming inefficient in PM. These logs affect the resizing and query performance. Moreover, to enable crash consistency, the persistency in operations, for example, cache line flushes and memory fences on the critical path can increase the latency. Next page, please, Andy. Okay, thank you. In order to address the log contention for concurrent hashing indexes for PM, we propose clever hashing, a PM-friendly and high concurrency hashing scheme. Based on now-level hashing, we explore write-efficient open addressing techniques to enable write-friendly and memory-efficient properties for concurrent PM hashing. Different from level hashing, clever hashing aims to offer scalable performance. In clever hashing, there are three main components. First, we design a multi-level structure without extra writes for insertion. Each level is an array of 8 slot buckets. Levels are added for expansion and removed when the rehashing in these levels completes. In each level, one key has 2 candidate positions via 2 independent hash functions. Since there are no data movements for insertion when the table is not being resized, hence, clever hashing is write optimal for insertion. Second, rehashing operations are performed in an asynchronous manner without blocking concurrent queries in other threads. Third, for concurrency control, atomic primitives are leveraged to enable log-free progress for all queries, including interleaved search, insertion, update, and deletion. Specifically, since we only store pointers in the hash table, it's possible to exploit the atomic visibility of pointers to enable the log-free concurrency control. Moreover, the crash consistency for log-free index can be achieved with small overheads. More details about the quietness guarantee are available in the paper. We implement clever hashing using PMDK with CPP bindings and compare with state-of-the-art PM hashing schemes. Results with YCSB on real Optane PM demonstrate the efficiency in throughput. That's all. Thank you for your listening.
Thank you very much, Zhangyu. Very interesting summary. The next talk summary is going to be from David. And again, we'll please type your questions into the chat window, and then at the end we'll have a panel of all of the speakers together. Go ahead, David. Here's your first.
Hi, can you hear me?
Yeah, we hear you.
Okay, perfect. Hi, I'm David Aksun, final year PhD student in EPFR, advised by Jim Rarus. We had a pretty good idea to build durable data structures that we were proud of, which we called in cache line logging. In cache line logging allowed an application to avoid explicit cache line writebacks in the fast path of the data structure and provided crash consistency. We decided to see how well it works. At the time, we didn't have access to Optane devices, so we used software simulation approach similar to the other papers. We published the paper in ASPROS, and we were happy about the outcome. Then Intel provided us with access to Optane-equipped servers. We went back and reiterated the in-cache line logging idea using real hardware. The results show that in-cache line logging is not suitable for deployment with the current Intel Optane devices. The goal of this talk is to explain why the measurements on Optane are different. Next slide, please, Andy. Here is the key result for evaluation on Optane. The figure shows the evaluation of the in-cache line logging approach using the mastery data structure with YCSP-A write-intensive workload. The blue bars show the baseline mastery and red bars show the in-cache line logging approach. We can either put the mastery in those structures, value buffers, and in-cache line logging mechanism on DRAM, which is shown by the DRAM bars on the left, or on Optane, which is shown by the Optane bars on the right. Or the bars show normalized throughput with respect to baseline mastery using DRAM. If we take the DRAM evaluation and compare baseline mastery with in-cache line logging, then the results are similar to what we have previously reported, as is indicated by the DRAM bars. This is what we expected. If we take the Optane evaluation and compare baseline mastery with in-cache line logging, the overhead of introducing in-cache line logging is similar to the ones reported in the DRAM evaluation. However, reporting in-cache line logging overhead just for Optane evaluation is not sufficient. Let me explain the reason. So please pay attention to the blue bars, both for DRAM and Optane, which use baseline mastery. The absolute performance difference of using Optane is significant. And on top of this, if we add the overheads coming from the in-cache line crash consistency mechanism, we will have an even lower throughput. Next slide, please. So let me explain why there is a significant performance gap. In-cache line logging requires the data structure to be in persistent memory. All the read and write operations that are done to the data structure have to use the Optane device. However, Optane is slower compared to DRAM and has limited read and write bandwidth. This is an inherent cost that cannot be avoided when putting the data structure in persistent memory. Adding any crash consistency mechanism that does prevent a lot of reads and writes to persistent memory will further incur additional costs. Our simulation technique focused on measuring the effect of cache line writebacks by allowing delays after the advance instruction. Therefore, we focused on minimizing the number of cache line writebacks and optimized the algorithm for the simulation. Next slide, please. As Swanson's and other groups' measurements indicate on top of ours, Optane in its current form is still slower and has limited read-write bandwidth compared to DRAM. In this talk, I'm taking in-cache line logging as a substitute for any crash consistency mechanism that does a lot of reads and writes to persistent memory, especially data structures that are modified directly on Optane. These types of data structures have to pay the cost of using Optane and incur an additional cost from the crash consistency mechanism, which is not a good idea at the moment. Finally, and most importantly, simulations can be misleading. Our implementation put the data structure in persistent memory, so we did a large number of reads and writes to persistent memory. Running on Optane led to elevated costs, which the simulation missed. The simulation needs to simulate everything about the real hardware. Other papers also use the same simulation technique. Sadly, we ended up optimizing the algorithm for the simulation. In the end, we got what we measured.
All right, excellent. Thank you very much. So now we'll go through and have a panel with all three of the speakers, and we can ask questions. The first question that came in actually was from Piotr, and Piotr, perhaps you'd like to just ask it live. I know there was some chatter on the chat window, but I think it'd be a bit easier just live.
Okay, I can do that. So my question was about the data set used to train the model that automatically made programs persistent. Because what I've observed on the talk is that the results that were shown were based on PMDK examples. And I'm assuming that the data set used to train the model actually also used those same PM examples. So then my concern is that the results might be a little bit skewed because the model could have simply remembered what was trained.
A very good question. Thank you, Piyush. And my answer is the training set is part of the PMDK example codes, and the test sets we have also tested our model on the open source LeetCode solution codes, and it also show very high accuracy. That it is the high model generalization ability to show our model can remember these changes. So actually, our model is trying to learn how to add these APIs or the policy to add the APIs from the training dataset. So more details can be referred from the full talk video on both training and test datasets and the details. Yeah, thank you.
Thanks.
Mm-hmm.
Very good. Let's see. Let's go on. We had a question for Zhangyu. Actually, Pio, you had a question for Zhangyu since you were just talking. Why don't you go ahead and ask that one?
Sure. So I'm one of the PMDK developers. So it would be cool for us if you could contribute what you worked on directly to PMKV. In this way, we can collaboratively enhance the system support that we have in PMDK. So the question is, would you consider actually contributing your work to PMKV? And then a follow-up question would be, are there any specific performance optimizations that you would want in LibPMJ or LibPMJ C++ that would help with your work?
Yeah, thank you for your question. And actually, during our design and research, we are working and checking the Hanxian map implementation in the PMKV, and we found that there are the original Hanxian map may use logs, and it may then it also use conservative lazy rehashing to defer the rehashing operations, and we conduct our work for the log-free in this design. But actually, this work is still under the code we publish is still a prototype implementation, and we are working on the virtual improvement, and it would be glad and we will be honored to cooperate with you and the PMKV team to contribute our work. If you and if you are interested, I think we can give more communication offline or talk in the emails.
Sure. I'm very happy to hear that. And if you guys want to contribute something or want to collaborate, we will be happy to do so. So maybe to address something you said, in CMAP, we use locking. And one of the reasons for that is because we found that using actual lock-free algorithms was extremely difficult to do correctly. And so that's why I'm very interested in your work, because it shows that actual log-free programming is possible in PM. Okay, thanks.
So, so Zhangyu, this might be a good time for me to ask my question because it fits really nicely with what was just being discussed. So, as you might be aware, there are machines coming in the future where the CPU caches are considered persistent. So, my question is about your work. Does it detect this case and just fall back to using the old single instruction, compare exchange when it detects that the CPU caches are persistent? Because now there's no need to do anything special for persistence and lock-free algorithms.
Yeah, that's a good question, and I think you talk about is what you talk about is EADR from Intel.
That's right. That's right.
Yeah. Yeah, I think for last week I also listened to the talk from William Wang from ARM, and I think what he talked about is very interesting. And if we have the EADR support for the total story order from the x86 CPU, we can directly use our code for DRAM profile platform to for the PM platform, and without much effort to make it quite consistent, because the cache, CPU cache is also, we can consider it as volatile, or is persistent. So I think if we have EADR, the programming and the use for the PM would be much easier. And maybe we can design a new hashing index or other data structures for PM. I think that's okay.
Okay, good. Let's see, let's move on to a question for David. Piot's question is so short, I'm just going to say it. Does your algorithm require cache line write atomicity?
So just to clarify, with cache line write atomicity, do we mean propagating the cache line to the persistent memory atomically? If so, yes, we do require cache line atomicity. Write atomicity.
Yeah, and I think Piot's asking this because at least on the current Intel hardware, you have ordering to persistence guaranteed within the same cache line, but
yes,
there's no 64-byte atomic write to persistence.
So we don't require 64-byte atomic at all. So
okay.
Not that write atomicity. We just need the cache line to propagate to the persistent memory as a cache line. We don't care about the write atomicity. I mean, the ordering of writes to the cache line is important, but propagation-wise, it should be 64 bytes.
Excellent. Thank you. Let's see. We had another question for Hanxian. Michael Scott, do you want to ask this question directly?
Sure. I'm trying to understand the use case for your intelligent tool. If I have data structures in my program that I want to make persistent, I think you're not assuming that I'm trying to make the entire program persistent so that I recover everything, including the PC. So there's some subset of my data that I want to survive in consistent form. Somehow I have to annotate accesses to that data to get the persistence right. And hopefully, if I know what I'm doing, I can go through by hand and do that, but it's really tedious and I might make mistakes. So maybe an intelligent agent gets rid of the tedium, and conceivably it makes fewer mistakes than I do, but that's the part I'm really skeptical about. How do I gain confidence that it's doing the right thing when it's trying to learn what my program means and I hopefully already know?
Hi, Michael, very good question. So actually, it's exactly why we want to make this framework. So our framework basically want to help the new users, like someone who didn't have so much experience on persistence-aware coding, and our project, our framework can help this persistence program to an extent, but you know, because machine learning is inherently approximate, so sometimes it can be also some failure or bugs after the generation, but the generated code can be further detected and checked by the debugging tools. So and we are still trying to improve our framework robustness and try to make more correctness. And how do I make sure if I correct? So our machine learning framework basically want to pass the workroom PMM check and PM reorder and get the feedback and make sure there is no error from the in the program running. Yeah, that's my answer.
Except that PMM check and reorder don't do end-to-end checking. You have to provide predicates for what you're looking for. So how do I tell them what it means for the program to be correct?
So in the training process, the PMM check or PM reorder will give some feedback, like the reports, like which lines of code is incorrect or impersist, and feedback to the neural network, and the neural network will modify its parameters and try to learn to eliminate that kind of reports in the new runs, in the new inserting APIs. Yeah.
Well, so to play on Michael's question a little bit, if PMM check produces a false positive, so there really isn't an error, what does your approach do, Hanxian? Do you have a way of marking something as a false positive that it shouldn't try to fix it?
Yeah, that's a very good question, because you know, actually the machine learning didn't know this kind of like false positive. It only know I want to try to eliminate the error in the PMM check or PM reorder. So yeah, this is still need to fix. Yeah, but after the generation, we can still check the generated code by some other debugging tools. Yeah. Yeah. Thank you. Very good question.
If I can add something, Andy.
Yeah, please.
So I don't think PMM check actually can return a false positive. Maybe it's my arrogance, but I think Michael had a good point. PMM reorder actually requires the application to specify the checking function. So if you have a queue, then you have to implement a function that checks for the invariance of that queue. And whenever the program that is generated, for example, inserts something in that queue, then the PM reorder will check against the invariant if that queue is correct, right? So I think, so what's missing here is that the information, how does the thing that you developed get that checking function? Does it implement it automatically also?
So was that a question that last?
Yeah. Yeah. Well, yes and no. I think I know the answer, but so I think the application developer still has to create the function that checks for correctness of the output algorithm, right? Because otherwise there will be nothing to test against.
Yeah, so Hanxian, I think what the comments have been doing, if I can try to give my take, I think there's a difference between where someone is clearly using an API incorrectly or using a programming model incorrectly, and you can detect that and flag it for them, and where they've got a logic problem in their program, but the APIs are all being used correctly, but they've got a logic problem, and the only way, I think what Piotr's saying, the only way to know that would be to also have them provide some sort of checking function that can say, here are some, things that should always be true that you can run this checking function for. And so, it doesn't seem like you could automatically generate the checking function, because it seems like you have to be the author of the code to know how to do that. I think that was also Michael's main point.
Yeah. We need to write some checking function in the PM reorder for each example code. Yeah.
To some extent, my question is a general question about intelligent agents. They're fabulous for approximate applications. You know, if I want to do web search and I want to know, you know, some web pages that have to do with this topic, there is no exact right answer. And an intelligent agent is a great tool. But if I've got something that has a notion of provably right and provably wrong, I worry about systems that try to produce code without actually understanding the right and wrong part, just kind of looking for patterns. So I have this kind of built-in skepticism and nervousness about the area, and that is betrayed in my question.
Like, would you want that code to be, you know, running your heart machine, right?
Yeah, or driving my car.
Driving your car. I think that's a good observation. Okay, so let's keep moving. Steve Heller, you had 2 questions for Zhangyu, if you'd like to unmute and ask those.
Yeah, basically, as a lot of people probably know, I've been developing some hashing software myself, and I always like to know what the competition is up to. So I was wondering, I know you mentioned that you weren't moving records during insertion. Do you move records during rehashing? That's the first question.
Yeah, for the answer, we did move items for the rehashing. Specifically, for our design, we use a multi-level hash function, and each level is an array of 8 slot bucket. And when the hash clearance cannot be addressed, because there are no empty slots in current hash table, we will add a new level, a new top level, which has 2 times as many buckets as the original top level, and then rehash the items from the bottom level to the new top level. This is rehashing progress. Yeah.
Okay, my other question is, does the performance decrease when you do this? In other words, if you rehash a number of times, is it going to get slower and slower, or what is the behavior under those circumstances?
Yeah, this is a good question. And because if we continuously add a new level, the number of levels will increase, and the number of buckets to check will also increase, so which will increase the search latency. So for current design, we use the background rehashing threads to continuously perform the rehashing. And if the buckets, the item in the bottom level are all rehashed, we can reclaim the level in that is the bottom level. So we can decrease the number of levels if the rehashing is finished. And for the read-heavy workloads or some workloads that is not read-heavy, we can guarantee that if we put more rehashing threads, the hash table can continuously rehash until there are only two levels left. So we can ensure we only need to check 2 levels to determine if the key exists in the table or not. So for short, for the read-heavy workloads, we can guarantee that there are only 2 levels to check, which can guarantee constant scale search latency. And for the write-heavy workloads, in our experiment, we find that 1 rehashing thread is enough for 35 worker threads, and the number of levels will not exceed 4 levels, and the search latency is still acceptable.
What kind of latency are we talking about for looking up, and what's your worst case average latency look like for retrievals?
Yeah, the latency I talk about is search latency, because and for other operations, for example, the insert or delete, they all need to check if the items it is in the table or not. So the latency will also related to the number of levels. And for the worst case, I think the worst case is to check all levels to find if the item exists. So the worst latency is to check all candidate buckets in all levels. So this latency is proportional to the number of levels in the table.
Okay, but it could be like, it could be a number of, the point is it may be quite a few microseconds then. I'm just trying to get an idea of the general speed of what you're doing.
Okay, actually for the specific number, in our implementation with PMDK with CPP bindings, we find that the search latency, the average search latency is several microseconds. That is mu s.
Okay, that's fine. Thank you very much.
Yeah, and I want to emphasize that because we use the PMDK with CPP bindings, and the CPP bindings may have some additional performance overhead compared with the PMDK of C version. So I think maybe for PMDK with the of C version, maybe its search latency can be further decreased. And we are still working on implement our scheme with the PMDK of the C version.
Good,
Okay,
good.
thank you.
Mm-hmm.
Thank you. Let's see, I had a question for David. You know, in your talk, you have kind of at the end, a sort of a summary of learnings and advice, things like avoid working directly with data structures in Optane. And we're certainly seeing a lot of these key value stores and NoSQL databases and so on that I think fall into two categories, which I would like to say one is immediate consistency and one is eventual consistency. And I wanted to know whether your advice was different between those, whether you thought that there was a different approach between those two, since immediate consistency really does mean you have to, you know, kind of micromanage the data structure in persistence. So I thought I'd hear your take on that.
So I would say for even for both approaches. So what I suggest is, so Optane is a wonderful device. It's byte addressable, it's fast, it's what we could have dreamed about. But both for immediate consistency and even eventual consistency, we want to avoid doing as many operations to obtain. I mean, we want to remove all the possible operations from Optane as much as possible. There are other concerns about variabling as well. But so, what we first of all, is this? Does this answer your question?
Yeah, I think so. I mean, I think you're just telling me that in both cases, it makes a lot of sense to try and combine operations in DRAM before you send them to persistent memory.
So exactly, this was going to be my second sentence. Yeah. Try to buffer the operations on DRAM as much as possible before propagating it to a persistent memory.
Excellent. That sounds like good advice. Let's see. I also had one for Hanxian. You know, because of all the observation that these persistent memory APIs and the low-level programming is error-prone, many people are building higher-level APIs, like a key value store that only has a set and a get. And so I'm wondering, you know, if I'm a programmer and I'm using one of these higher-level APIs where, you know, it's pretty hard to make an error, do you still see an application for your work, or do you think that your work really applies to the low-level programming?
Yeah, thank you, Andy. Very good question. So I would like to say if you have a even more friendly APIs, but users still need to like learn how to use API, and he may also requires a memory knowledge to make sure he's correct. And moreover, I think a more friendly API means maybe more overhead when doing the coding. So our framework based on the lower level API may have higher efficiency. Yeah, that's my answer.
Very good. Thank you.
Yeah,
Let's see, I think we've gotten through all the answers in the chat window, but we still have some time left if anybody else wants to raise any questions for anybody on the panel. Anybody else?
Andy, this is Jim. I asked the question first week, and so I'll ask the question to all three of the panelists. So there's a lot of different things that you could focus on, especially advanced research that all three of you are doing. What makes persistent memory so interesting, and why would you pick that over, all the other dozens of really cool technologies that are out there?
So Hanxian, do you want to answer that one first?
Sorry, I didn't get the question. Can you repeat the question again, Jim?
So what I said, Hanxian, is that there's a variety of really cool technologies out there, and you as a PhD student could do research on a variety of things. So what made you choose persistent memory? Why is that more interesting than all the other choices?
Okay, so actually, yeah, persistent memory is kind of new application for me because actually I'm a new second-year PhD student, and actually, like the machine learning-based translation has been very well investigated on other application like translate between C or C++ or Java or Python, other kinds of language, but there's no machine learning based algorithm for persistent memory aware programming because it's I can say it's a very relative new area for me, and there's still many challenges in this kind of translation. So one problem I met in this project is since it's relatively new, there's no well-prepared data set. There's no bunch of data sets for me to train the model. So I need to change the conventional supervised learning to the reinforcement learning. So there's more challenges in this new area and more interest me. So that's why I chose this application. Yeah, that's my answer. Thank you.
How about you, Zhangyu?
Actually, for our research group, we all did the research on NVM or persistent memory. So that's the basic reason why we conduct research on persistent memory. But during our research, I also found that because the persistent memory is different from the DRAM, and it with persistent memory, we can think that the persistent layer is moving up to the memory level. So all the hardware architectures or the software system can need to consider the change or the modifications to persistent memory. So there will be many opportunities and challenges for our computer systems. So that is also very important and interesting. So that is the reason why I choose the persistent memory as my research direction. I think that is my answer.
Excellent. How about you, David?
So when we think about persistent memory, we always focus on the fastness of the device. Let's take this device, let's add some crash consistency to a data structure, and let's make it persistent. Or we can take an existing database, and with some minor modifications, we can really get high throughput using the obtained device. But what really got me interested in persistent memory and what keeps me awake at night is the programming model. So how are we going to program the future, software in the future? So, I'm thinking, so will we integrate PMDK into the Linux kernel? Will we have special persistent types in the Linux kernel? So how are these things going to evolve? And this part of persistent memory really makes me interested, and it keeps me keeps me persistent.
Excellent. Yeah, it seems to be there's kind of two takes. There's the people who are trying to sell persistent memory who say, oh no, there are new challenges, what are we going to do? And then there are the people who come to this conference who are saying, oh yes, there are new challenges, let's let's grab onto these and figure out what to do. I'm really delighted at the kind of research that we see going on here. It's really fantastic.
I'll add to that, Andy. I'm very heartened by the level of research that I'm seeing going into this. Even a couple years ago when I started getting involved with SNIA and working on persistent memory, a lot of it was very much, okay, well, let's do theoretical research on how to persist memory. Now it's really let's get into practical research on applying software methodologies to persistent memory. I think that switch is very heartening for the industry, and I think it's going to make a big difference in terms of some of the future research.
I totally agree. Let's see, we do have one more question come in for Zhangyu. Jan, do you want to unmute and ask the question directly?
Sure. So my question is about loads, basically, because as far as I see the solution, when you want to read a value from a data structure, you need to search at least 2 levels. That seems twice as much as on ordinary maps. So basically, in work loads dominated by loads, are you still the structure of choice, or should I look for a different solution?
Yes, that is a good question. Thank you for the question. And actually, we do not have additional optimization for the read-only or the load-only workloads. Basically, we in our current design, we assume that for hash table, if we want to search a key, that we only need to check the 2 levels, and the worst case is to check the most full buckets. So I think we can guarantee that the worst case for the search operation is still a constant scale. So I think maybe the performance.
I get it that it's like constant scale, but it's still you need to do like to look up 2 levels instead of 1 level in your ordinary map. You just need to look at 1 level and probably a short list of possible values. And here you have 2 levels and 2 hashes. So basically you access like 4 locations for a single load, right? So does it show up in the results as a drawback of your solution? How can you compare against, what's the result of comparing against, I would say, more naive maps?
Yeah, I think if we want to further improve the search performance, one possible solution is to add some filters, for example, the balloon filter or the metadata information to indicate whether the key is this in current level or any level. So with this information or hint, we can directly look into that level to decrease the search latency. That is my current opinion for the further optimization.
This is Chen from FutureWay. I have a different opinion on the Bloom filter usage. I don't think Bloom filter will be helping the case, because our experience with Bloom filter is to get a good means minimum false positive rate, you need multiple hash functions. Like we use 3. So that means three distinctive memory accesses. They're going to miss L3 most likely. So that is 3 memory access that's not going to be good. So for in my view, the load heavy workloads, we can somehow do something which, when I look at the levels, if we just have one level, that would be optimal, right? Then we have a overflow place to hold the occasional writes. That's something I'm contemplating while hearing this. But for heavy ones, then it makes sense to cascading them. Then there must be a middle ground or trade-off to combine the two, that like automatically transit from one or another, or we can use some kind of learning or feedback loop. That's
Thank you for your comments. I think that is a trade-off between the number of levels and the size of, you mean the trash? Okay. Oh, no, sorry, stash region. If we have less levels, so the latency for search can be decreased.
Yes. But it comes down to how many L3 misses that we will incur with this those data structures.
Okay.
Very good. I think we just have enough time for a last question that Steve Heller asked, and I'm just going to read it. Does the time taken to search in each level depend on the size of the level? This is for Zhangyu.
Actually, not, because we use hash functions to determine the candidate buckets in the level. So for with 2 hash functions, the time to locate the buckets is 2 memory access. So the time is constant, I think.
Very good, thank you. I really want to thank Hanxian and Zhangyu and David, all 3 of you. I think all 3 of your talks were very well done, very interesting, and I appreciate the interesting conversation.